Hi, this is Dima Brook, CTO of XP.NETWORK, and today we're going to speak about prime numbers in the first part of the video, and then creating Schnorr private and public keys. Everything will be done in Rust, therefore I created a folder that I called Rust, and we'll do everything here. So first let's create a repository, and let's call this repository, let's say cargo new, and let's call it primes, like so, and we have this folder here like this. Alright, so let's get into this folder, primes like this. Let's check that we're in this folder. Alright, so right now there's nothing in this folder except this print line. So for example, if it's a cargo build, we'll just see this hello world. Let's say cargo run, and there it is, hello world. Right. So we're going to replace this code with a code that works with prime numbers. This was the topic of our previous video, and here I'm going to demonstrate you the problem with prime numbers, why it's so hard to work with them. We will initially work with prime numbers from 0 to 1000. We will quickly find them, and then we will see what happens if we start working with a big number prime numbers, and you will see how slow and how hard it is, and that is one of the keys why elliptical curve cryptography is secure. So the first thing we will have to do is, let's do this. So let's go to cargo toml and add some dependencies. So of course I prepared for this video, so I made sure that I already know the latest versions of the libraries. That's why I just copy pasted them here. And this is what we're going to need. So num bigint, num traits, and termion. Those are the libraries that we're going to need right here in our main file. So we won't make any subfiles here. We'll do everything in this file. So let's do this. So first let's import all the necessary components that we are going to use here. So here we will import this object that creates a big integer number. That's something that we will need later on. Okay, also this one converts a big integer to unsigned integer. Okay, here we use primitives, and this will allow us to erase old lines so that we can write the result in the same line, so that we won't have a huge list of results, which will be hard to read, because we only need the information that is relevant to what we're looking for, not all the information that accompanies it. So that's why we're using this instead of built-in print line macros of Rust. So first let's write a function, and actually I guess I'll just copy paste from what I prepared before, not to waste time on typing. So this little function just checks whether this number is even, and if that's the case, it returns true. If not, it returns false. Okay, so if we have a value and this value is even, then this part of the function will return true or false. If there's no value, then we will just get false as a result of this. Alright, so let's go here. The next function that we're going to use here is called isPrime. So what it does is it checks whether the number is a prime number or not. So it takes a number as a big integer, because later we will work with big integers. In the beginning the numbers will be comparatively small, and then what it does is this. So if it is equal to 2, then it is a big number and it quickly returns true. If it's even, it returns false, because even number can be divided by 1 by itself and by 2, so it doesn't meet the requirements of a big number definition. And then we have the word 2 that represents 2 as a big integer, and we have a mutable I, like an iterator that will run. Okay, it starts with 3 because after 2 the first prime number is 3, and then we just run a loop and we check if the numbers up to n are prime numbers or not. We also make a step of 2 to exclude all the even numbers from the loop. This is how we already remove at least 50% of the numbers that we know for sure are not prime, and this makes our script a bit more effective. This is by no means the most effective script for finding prime numbers. It doesn't even try to be one. It just, the purpose of this is to show you what the problem of working with big numbers is. That's the point of this video and this code. There are several different algorithms that look for prime numbers in a more effective way. Some of them find prime numbers quicker, but they omit some of the potential prime numbers because they have a special algorithm of looking for them from the prime number theory. Some of them are more meticulous, they check more versions, but they're slower. So the purpose of this video is not to show you how to properly and effectively find prime numbers. The purpose is to show you why it is problematic, and maybe partially to show you an extent of how problematic it is. So let's write the main function from which we will actually call everything. So this function, I guess I'll have to be writing for you to see what I'm doing. Okay, in this function I'll be actually calling the functions that we wrote before. So let's do this. To begin with, let's do this. So to begin with, let's start from those. So the start will be, actually we can begin with 2. Alright, fine, we will begin with 3. So what we will do is we will see what prime numbers we have from number 3. Here we represent it as unsigned integer with 64 bytes up to 1000. Okay, I know that type is a bit excessive for such small numbers, but because we are going to use bigger numbers later, we will leave this type for compatibility with the big numbers. Okay, also let's do this. Let's introduce a step. So at the beginning the step is equal to 0. As you can see here, we define it as 0 of type unsigned integer 64. This will help us see at what step we are now, just to know where we are in the loop and how many steps we already made. Okay, let me again copy paste some more items here. I will also explain to you later what they are to avoid typing. Okay, so the current number is equal to start, and we will increment it. We also have two numbers 1 and 2. Again, we just create them from unsigned integers. And studio out will let us output the result in a custom way, not using print line. So handle is also required for outputting information in the terminal. And let's actually start the loop. So inside the loop we will do the following. So while our current tracker is less than the final number that we are interested in, we will so you see we're using this handle that is required for this write macros. Also, I added this let underscore because otherwise Rust complains that the result of this macros is not used anywhere. Like I can show you. For example, if I remove it, like so, it starts complaining that the result is not used anywhere, and then when we return it, it stops complaining and we have a clean output that will not interfere with the results that we're looking for. So what we're doing here is we're showing at what step we are, just to know how many items we have left. Okay, then we remove this line, and then we check if the number is prime, then we will write a prime number and the number itself. Okay, then we add 100 empty spaces, because this line is much longer than this one, and in order to erase everything from this line, we have to make a long line that will erase everything here. Then we increment our current by 2, so we have a step of 2 to remove all the even numbers, and then finally we will just write a new line so that this line in the terminal is not in the same line as the last line of our result. So let's actually build it. Cargo build and cargo run. Okay, you saw how quickly it was. Actually, I'll do it like this. We don't know how much time it took, so we'll do this time cargo run, and this is how we will know how much time it took for us to get all the results. Okay, so here we go. So we looped from 3. Let me find the beginning. Yeah, from 3, and we see all the prime numbers. You can actually go to Wikipedia and you can find all the prime numbers up to 1000. I deliberately selected this range for now, just to be able to meticulously check that I'm still getting all the prime numbers. I'm not missing anything, because when we go to very large prime numbers, it will be very hard for us to check. It will be very computationally intensive. And this is why I took the small numbers, just to be able to check. And as you can see, we go meticulously one by one. We found all the prime numbers from 3 up to okay, so before 1000, this is the last one, 997. Okay, and we see that this it took us 499 steps, because we were going with step 2. So we only checked the odd numbers, and the current is 999. Obviously 1000 is not prime because it's even, and it took us altogether 0.229 seconds. So it took us less than 0.3 of a second. So now let's do the following. Now let's change a little bit, and you will understand why I had all these things that we didn't even see here. So let's replace 2 lines here with this. So we are not going to check prime numbers between 3 and 1000, but we're going to check prime numbers between, oops, just a sec, more lines here. Okay, so we're going to check all the prime numbers between 2 to the power of 64 and 2 to the power of 128. Right now they are big numbers, so let's see what we're going to get out of this. So we don't need to see this code anymore. I'll just show you. Just let's clear the terminal. Let's say cargo build, and let's clear it. Time cargo run. Okay, so as you can see, we are making a lot of steps and we're not finding a single prime number. And the growth of how many steps we're going to need here grows exponentially, because we have 2 loops. Okay, now we can put it down. We don't see much of output. Okay, and this is only the problem of finding prime numbers while we're dealing with very big numbers, right? So why do we have 2 loops? Is because we have 1 loop over here, in our function isPrime, where it checks whether this number is prime by trying to divide it by itself and seeing that we are getting the right result. Okay, and we have another loop here while we're looping through odd numbers. So this is a very inefficient and computationally expensive algorithm that looks for prime numbers. So this illustrates how difficult it can be for someone to find just the prime numbers for the equation, and then you will have to put them into equation and check that the equation meets the requirements that are set by the encryptor. So this can run actually for a very long time, for days I guess. I'm using a Mac M1 here, and it will take days or maybe weeks to find them. So this is how hard it is from a computational point of view. So what I can do is I can show you, I can close this window for now. I can show you an example when I just ran out of patience. And for example, I ran it for 44 minutes. Let me see if I can make it bigger for you to see. Okay, so let me try to enlarge it. So I ran it for 42 minutes, and it took me, let's see, 278 million of operations, and I still haven't found a single prime number. So I just ran out of patience. I just switched it off and decided not to continue, but and as you can see, we're still running and never getting a result. So this video proves that working with prime numbers is very difficult, very computationally expensive, and it's a part of the protective measures that cryptography brings us as a technology to protect our signatures. And this is partially how our validators make sure that nobody either replays their signatures or pretends to sign on their behalf. Well, that's it for this week. Next week we will keep speaking about Schnorr signatures. Don't forget to subscribe. If you like this video, please put a like below it. Thanks for watching, and see you next week.